It's my pleasure now to introduce our speaker today, Professor Catherine de Kleer, an assistant professor at Caltech. Catherine is one of my former highly successful graduate students. She finished her PhD in astrophysics at UC Berkeley in 2017, which was focused mostly on spatial resolution observations in the infrared of Io, one of Jupiter's 4 Galilean satellites. She always had a very broad interest, which, for example, led her to attend several summer schools in astrobiology. After leaving Berkeley, Catherine was in the first cohort of Heising-Simon 51 PEC Fellows, during which time she expanded her research to the neighboring Galilean satellites, and she started using the VLA and ALMA. So today, Professor de Kleer will be talking about the surface environments of the solar system satellites. And without further ado, I now turn the control over to Professor de Kleer.
Okay, well, thank you very much, Imke, for the kind introduction, and to the ngVLA and NRAO for inviting me to give this talk. I'm happy to be here and excited to talk to you all a bit about some of the most interesting objects in the solar system, which is the moons of the outer solar system's gas giant planets. And in particular, I'm going to be talking about their surface environments. And I'm using this term fairly broadly to encompass, for example, the surface composition, whether or not they have atmospheres. If so, how dense are the atmospheres? What are they made of? Is there precipitation? Is there liquid on the surface? And is there, let's say, tectonic or volcanic activity? So these are the sorts of detailed questions that we are now able to study on solar system moons, and characterization of the solar system satellites, sorry, advancing slides, of the solar system satellites is one of the current frontiers in solar system exploration. And we're starting to look at these individual worlds and understand their unique properties, this sort of diverse array of objects that we have in the solar system. The first generation of spacecraft missions were largely focused on the planets, but data that came back from, for example, the Galileo mission to the Jupiter system and the Cassini mission to the Saturn system has just shown us how unique each one of these moons are, from the methanological cycle on Titan to Io's volcanic activity. And as I'll come back to at the end of the talk, the next generation of spacecraft missions includes many missions that are optimized to study in detail individual moons. So in this talk today, I'm going to be focusing on radio interferometry observations and of the solar system moons and what we've learned from them, and in particular with ALMA. So I'm going to focus in particular on 2 moons and some very recent work on those moons. But before I jump into that, I want to highlight just a couple of really neat results on 2 other moons that I'm just not going to have time to go into in any more depth, but I just want to present quickly. So the first of these is Titan. Now, Titan is one of the moons that was studied in great detail by the Cassini mission, and it is, in some sense, the object in the solar system that is most like Earth. It has a dense atmosphere, it has clouds, it has liquid on its surface, it has precipitation. But the difference is that the liquids on its surface and the clouds in its atmosphere are made of methane and hydrocarbons. And so we have a distinctly different type of volatile cycling that's going on Titan. There's also quite a bit of chemistry, and in particular organic chemistry, that's going on in Titan's atmosphere. So Titan has gotten a lot of interest as a astrobiologically relevant target. And people have thought about, what would life look like on Titan's surface if we could have life on Titan's surface? Well, the liquids that Titan has on its surface are hydrocarbons, and so you couldn't have microbes as we know it on Earth, but what sorts of molecules are available to form microbes, for example? And one molecule that's been hypothesized is vinyl cyanide, H2C2H3CN, that could potentially form in Titan's lakes and could be a cell membrane for some, alien life form. And this species was tentatively detected by the Cassini mass spectrometer, but they were unable to ambiguously identify it. And it took an observation with ALMA by this team that's shown in the reference to unambiguously detect this molecule vinyl cyanide for the first time. Europa is another moon that has gotten a lot of interest from an astrobiological perspective. You look at Europa's surface, all these stripes that you see across the surface are tectonic features and maybe regions also where we have exchange of either heat or material between Europa's surface and its subsurface ocean. Now, the Galileo spacecraft, which visited the Jupiter system, took a thermal image of Europa at night and found this hot spot on its surface. So that's shown in this image here. This is Galileo data. The circle is the size of Europa, and you're looking at temperature residuals from a model for the surface temperature. And so that red blob that's pointed at is this hot spot. And they said, oh, maybe this is a region where you have enhanced heat flow. There could be heat coming up from the interior. Maybe this is a region of enhanced material exchange for between the ocean and the surface. Maybe this heat could, provide energy for life. So a team led by grad student Samantha Trumbo at Caltech looked at this same region with ULMA, where you also can detect thermal emission when you look at the continuum emission, and they looked at the exact same spot during the daytime. And instead of appearing hot, that same region appeared cold. So if you had a region of enhanced heat flow, you would expect it to be hotter than it should be during both the day and at night, but instead it's hot at night and cold during the day, which tells you that instead of it being endogenic heat flow, it's actually a region, most likely a region that has different physical properties than elsewhere on the surface. And in particular, a higher thermal inertia, which if you're not familiar with that term, it's exactly what it sounds like. It's a material that resists a change in temperature essentially, and so it stays colder during the day and stays warmer during the night than it otherwise would be. So I'll note that both of these are examples of tentative detections of interesting phenomena that were made by spacecraft, but it took ground-based observations, and in particular ULMA, to either verify or in this case refute these tentative findings. So for the rest of the talk, I want to focus on two worlds that are not so much on the astrobiology of it, but on the geology and the physics. And this is Io and Ganymede. So Io, I've kind of subtitled a tidally powered volcanic world. And Ganymede, we're going to look at from the perspective of a planet-like world that's orbiting within a planetary magnetosphere. So starting with Ganymede, Ganymede really is a planet-like world. It's intermediate in size between Earth and Earth's moon, and to order of magnitude, you could say Ganymede and Earth are the same size. It's also the largest moon in the solar system. And importantly, it is the only moon in the solar system to generate its own magnetic field. And this is particularly interesting because it's orbiting Jupiter, and Jupiter has a very strong magnetic field that is densely populated with electrons and plasma. And Ganymede is the actually only example we have in the solar system of an object that generates an internal magnetic field that is embedded deeply within the magnetic field of the object that it's orbiting. And so this sets up these really complex interactions. This schematic is showing graphically what the resultant magnetic field would look like at Ganymede due to the fact that it has this internal magnetic field that's embedded within Jupiter's magnetic field. And so Ganymede is a place where we can go to answer this question of how a magnetic field affects the resultant surface and surface properties of a moon or even a planet. And so just like how the Earth's surface is shielded by its magnetic field, Ganymede's equatorial regions are shielded by its magnetic field, but you can see that the magnetic field, that charged particles can access the surface in the polar regions, and even in the mid-latitudes, they get down to 30, 45 degrees latitude. You also see that this distribution of where the magnetic field lines access the surface is pretty asymmetric between the different sides of the moon. So Ganymede is tidally locked, meaning that it's always facing the same face to Jupiter. And so it has this preferential hemispheres. It has a front hemisphere and a back hemisphere effectively in its orbit, which we refer to as the leading and trailing hemisphere. And this leads to a different distribution of the magnetic field interactions over the course of the planet. And so we were interested in looking at how the magnetic field would alter Ganymede's surface, and in general, how the other processes that are going on Ganymede might alter its surface properties, and in particular, which processes would be dominant in altering the surface properties. So ALMA is a fantastic tool for studying planetary surfaces as well as atmospheres. And we observed Ganymede with ALMA, and when ALMA looks at Ganymede, this is what it sees. And I know that showing a UV plot in a talk is about as inadvisable as making a slide full of equations, but this is a radio astronomy hosted seminar, so you all are going to have to deal with it. And I'm showing it because I think it's a beautiful demonstration of the type of data you get from ALMA. It's so clean and has such high signal to noise. You see so many nulls in the UV curve, and this is a fairly clean looking Bessel function, which is just roughly the Fourier transform of Ganymede, which is to first order a disk. So you can see, though, that there are some features on this image of Ganymede, and that ellipse in the lower right-hand corner shows the beam size. You can see that there are some features on Ganymede's surface that don't strictly follow the kind of uniform disk. Hopefully that's coming through clearly over Zoom. And I point them out here in case it's not coming through too clearly, but these are regions that appear colder than the rest of the disk. And at least in one of these cases, the one on the right, that is a bright impact crater. And so, well, it's cold because it's bright, and so there's just not a lot of sunlight absorbed. So if we want to actually understand whether regions on the surface actually have different physical properties, or whether it's just they're brighter and so they're absorbing less sunlight, we need to build a model to try to predict what we're going to see and make a comparison. And I'm going to, in one slide, walk you through, hopefully fairly simply, what is actually a very complex modeling process. And this is something that's been done to interpret radio astronomy data of the planets for 50 years. It's just that decades ago, the only things that you could really map with a radio telescope were the moon, Mars, the planets. And now with ALMA, we can, and the VLA as well, we can get reasonably good spatial resolution on something as small and far away as Ganymede or Europa. So this modeling essentially works like you set up boundary conditions, you have some heat flow from the bottom of the surface, you have a boundary condition on the top, which is how much sunlight you absorb on a given pixel, and then you build a little numerical model where you conduct and radiate heat up and down to balance the heat flow through the subsurface. And this allows you to predict what the temperature is as a function of depth within the subsurface everywhere on the surface at every time of day, which is great. And then there's a third step that you need in particular for radio data, which is to integrate the emission that you get through the subsurface. So at radio wavelengths, millimeter, centimeter, you see into the surface a little ways. The surface is reasonably transparent to these wavelengths. And you, in something that has, let's say, an icy surface like Ganymede, you're maybe seeing tens to even hundreds of wavelengths within the surface. So tens of centimeters to meters within the surface. And the amount of emission you get from a given layer is attenuated as you go down deeper in the surface, but you need to sum all of these up, and then you get a nice model of the temperature that you should see. So this is the data that I showed before with that impact crater shown with a little arrow. This is the model, which to first order is indistinguishable, but you may notice that that impact crater doesn't show up as cold in the model. And if I take the residuals of the two, you can see that there are some areas that the model doesn't do a good job of. So the equatorial regions are warmer than the model, polar regions are colder, and these impact craters show up much colder than they should be from albedo alone. So the brightness of them cannot explain how cold they look in the radio. You need some kind of different physical properties. And we made these observations at a few different frequencies and on 7 different occasions where we got different, we're able to view different longitudes on Ganymede's surface. And if you combine those all and project them into a map, the top panel is what you see. So this is the temperature residuals from that model all across Ganymede's surface. And anywhere that you see a high temperature residual is a region that has different physical properties than elsewhere on the surface. The reason that I'm just showing you temperature and not actually a plot of physical properties is that there ends up being some ambiguity where a region that's cold could have lower emissivity, or it could be more dense, or it could be a more conductive material. So there's a little bit of finessing that has to be done in the interpretation, and this is kind of the raw result here. But you can see that first of all, the impact craters definitely show up as these cold spots that you can see here, and you can see on the albedo map on the bottom what kind of corresponds to what between the temperature residuals. But in addition to that, there's symmetry that you see here. There's regions that are too warm that are centered in the middle of the two hemispheres. So these are the leading and trailing hemispheres, the right and left half here, as well as in latitude. And so for an object that's tidally locked, when you see symmetry about the center of the leading or trailing hemisphere, this is a pretty good suggestion that you have some exogenic modification, so some kind of bombardment process. The plasma is hitting Ganymede's trailing hemisphere while its leading hemisphere is sweeping up neutral material, and so you can end up with these symmetric distributions. And at the same time, you notice that these mid-latitudes are anomalously cold, and those are the mid-latitudes where you see the strongest, the most magnetic field lines bringing charged particles to the surface. So the distribution of residuals we see can't be explained here by any individual process. It doesn't quite match the distribution, but it's very intriguing that we see these symmetries, which are very suggestive of some bombardment process that is modifying the surface properties across the surface. And that kind of sets us up for the next experiment to try to understand what the physical mechanism is that is doing this and how that operates. So you may have been wondering in the past couple of minutes, where is all this material coming from that is bombarding Ganymede's surface? And it turns out the answer is Io's volcanoes, which brings me to the next topic, our tidally powered volcanic world. So Io is the most volcanically active object in the solar system. Its volcanism is driven by tidal heating, and I'm not going to talk about tidal heating now, but I'm more than happy to discuss it in the Q&A section. Io's volcanoes are also the source of all of this material that is leaving its atmosphere and going out to populate the Jupiter system. And that material, and specifically how Io's atmosphere is produced, how that material is all produced, is the topic that I want to talk about today. So Io's surface processes are fairly complex. This is a sketch that was put together 2 days ago by James Keane, and he very kindly allowed me to use it in this talk. And there's a lot going on, and I know the labels are too small to read, and it doesn't really matter. I'm going to direct you to the things that are important, because as I said, I want to focus on the atmosphere and how the atmosphere is created. So Io's atmosphere is sulfur dominated. It's primarily SO2. And there are a few ways that SO2 is being produced on Io. You see these tall umbrella plumes here, and those plumes are volcanoes that are outgassing sulfur dioxide as well as other species into the atmosphere. Now that SO2, some of it freezes out onto the surface, and then you have this condensation sublimation labeling here, which is showing that you also have the SO2 surface frost sublimating. And so you have a sublimation supported atmosphere, but also a volcanically outgas supported atmosphere. And one of the big questions that we've been trying to answer for many years is there a dominant process that is driving Io's atmosphere, or is the dominant process time variable, or are there processes we're not even considering? So we want to try to unravel how much of the atmosphere is produced by sublimation and how much from volcanoes. And there's a really neat and convenient property of SO2 at Io that makes this possible, which is that SO2 is very close to, or Io's surface is very close to the freezing point of sulfur dioxide. So close that during the day, the SO2 can sublimate and support an atmosphere. By the way, the atmosphere I'm talking about is still very tenuous. It's nanobars in pressure, but it is sufficient to detect. So the SO2 can be sublimated during the day, but at night it should all freeze out onto the surface. In contrast, of course, the volcanoes don't care whether it's day or night, they're always outgassing. And so this means that if you can observe Io's atmosphere during the daytime and at night and make a comparison, you can actually control for these different contributors to the atmosphere and figure out the relative contribution of the two of them. So this is something that we did with ALMA. Oh, God, I'm expecting a different slide next. Sorry about that. So I just wanted to show really briefly what that viewing geometry looks like. So we can't actually observe Io's full night side from Earth because Earth is so close to the sun. that it's effectively next to the sun from the point of view of Jupiter. So you can't see the night side, but what you can see is Io when it's in eclipse. And this animation, which I hope is coming through virtually, shows Io coming out from behind Jupiter's limb. It passes through eclipse. The eclipse it lasts an hour to an hour and a half, and then it comes out into sunlight. And so this eclipse period is when we are able to look at Io in the absence of sunlight and see whether the atmosphere has frozen out and see what remains. So we did this experiment with ALMA just a few years ago, and this work is in review, and the analysis is led, as you can see, by Imke de Pater, who is our host for the talk series today. This is what Io's atmosphere looks like in sunlight. So the big circle is the size of Io, and you're looking at the SO2 emission. So you can see that there's a broad and fairly continuous swath of SO2 emission around the equator. There's not so much at the poles. It is a bit blobby, but you do have a broad background. The blobbiness is labeled with these letters, and everywhere in these little postage stamps that you see, letters is where there are volcanoes on the surface, and so we've tentatively attributed these blobs of emission to those volcanoes. So what happens as Io passes from sunlight into shadow? Well, you see that broad background atmosphere slowly disappearing, and all you have left is this blobbiness, which is coming from the volcanoes. So this is roughly what we were expecting, but let's verify it by looking at it the other way around, from eclipse into sunlight. And these observations are now made on a different date because you can't get both of these geometries at the same time of the Earth year. So here we are in eclipse, passing back into sunlight. And you can see, again, in eclipse, all you're really seeing is this SO2 emission from the volcanoes. And then as you pass into sunlight, the bulk atmosphere reinstates, and you see again this broad, bright swath of emission in the equatorial regions. So this is, although there has been evidence that Io's sublimation supported atmosphere collapses in eclipse, this is the first time that the atmosphere has been directly imaged and spatially resolved as Io passes from sunlight into eclipse and eclipse into sunlight. So this is the first really direct imaging, in a sense, verification of this happening, where you can see for yourself the sublimation atmosphere disappearing. And from this, we inferred that at least on these dates of observation, something like 30 to 50% of the atmosphere is coming from the volcanoes, and the remainder is coming from the sublimation. Now, the caveat is that Io's volcanoes are very time variable, so that percentage probably varies a lot in time. But it's interesting that both components of atmospheric support do seem to be providing roughly equal, let's say, contributions to the atmosphere. So this is a really neat and clean result. It's a little too clean, and so just for fun, I have to show you some mysteries that have also come up from the data. So these are, on the left is the SO2 image that I showed before in eclipse. Remember, everything should be volcanic in eclipse. And some of it is blobby, as I've said. However, there's a lot of emission, just sort of background emission, and emission that's coming from places where there don't seem to be active volcanoes, and we don't really know where that emission is coming from. It is possible that there is a lot of subsurface interaction, magma outgassing, magma interacting with SO2 frost that is leading to gas coming out of the surface through fissures, not associated with any volcano. And this is a theory that we're not really going to be able to test, I think, until we actually have a mission at Io observing in that really incredible detail. But on the right, so we also observed the gas species KCl, which also should only be present in volcanic gas plumes. And as you can see, there's no kind of background atmosphere here. There's just a blobbiness. But these images were taken during the same observation. I apologize, I just see this now, the spatial scale is different between the two, but the circle is the size of Io in both cases. And the emission is not co-located. And this is an interesting geological problem where you must, in both cases, the volcanoes must be responsible for the gas emission, but there are different volcanoes producing the KCl versus the SO2. So that's something to be investigated more from the geological perspective. All right, so as I start to wrap up here, I want to just back up a little bit and articulate the broad questions that these 4 examples, Europa, Titan, Io, and Ganymede, kind of fall under the headings of. So the first first broad question that we're really trying to answer here is, what are the characteristics of these subsurface ocean environments and of the worlds that host them? And we have only come to appreciate kind of recently how ubiquitous these subsurface ocean environments are. And we don't really understand what their properties are yet. Of course, one of the big questions is, are they habitable? Related to that question, how much exchange of material and of heat is there between the ocean and the surface, and the ocean and the mantle? And then particularly related to Io and Titan, what is the volatile inventory of the moons, and how are these volatiles cycled and ultimately lost? So Earth has the water cycle, Titan has the methane cycle, Io has an SO2 cycle. How can these sort of volatile cycles look? How broad of an array of these do we see in the solar system, or even beyond the solar system? So you don't have to take my word for it that these are big, interesting questions. You can look at where NASA and ESA are spending their money at the moment. And there are several major missions that are being planned to the solar system satellites, and in particular these icy ocean worlds. So NASA is planning to go to Europa with the Europa Clipper mission. There's the Dragonfly mission to Titan, and the European Space Agency is sending the JUICE mission to Ganymede, Callisto, and Europa. And all of these are scheduled to launch in the 2020s, and they are going to be answering questions about the potential astrobiology, habitability, as well as geological activity and volatile cycles, just all these same questions that are within this framework that are articulated. And even beyond these, NASA announced this year that they selected 4 missions for future study, and 1 or 2 of these missions may actually get to fly. We'll know in the near future. And 2 of these missions, 2 of the 4 that were selected for future study, are targeting solar system satellites, 1 Io and 1 Triton mission. And so hopefully you can see that there's a big convergence, I think, towards understanding the detailed aspects of the solar system satellites. So how do ground-based observations and radio observations fit within this context? So I'm trying to articulate that a little bit with the schematic that's shown here. So this little schematic is spanning several orders of magnitude in frequency, and just shows a couple of key relevant instruments that are being flown on some of these missions, in particular Clipper and JUICE, in the kind of thermal and surface study regime. And so in the infrared, you have the thermal imager on Europa Clipper, Euthemis, kind of overlapping with where the James Webb Space Telescope will observe. JUICE will be carrying a sub-millimeter wave instrument for studying the surface, but then there's a huge gap, orders of magnitude frequency gap, before you get to these ground-penetrating radar systems that are going to be carried by both Clipper and JUICE to study the deep subsurface. So the labeling on the left, surface and kind of depth within the surface, is giving kind of a order of magnitude sense of how deep you see within the surface over these different frequencies, and and atmosphere if present. The same kind of applies in an atmosphere if you have a dense atmosphere like Titan, which is rare among the satellites, but relevant for Titan in particular. So there's this big frequency gap, and hence gap in depth coverage, that is going to make it difficult to reconcile the data on the different ends of the spectrum here, which of course are wonderful radio facilities fill in really nicely. And you can raise this a little with the ngVLA and ALMA band 1, I'll drop it a little bit. But these really fill in a key gap in frequency coverage that we don't have otherwise, and will be very helpful in connecting the observations that we have of the deeper surface with the shallower surface. Beyond that, it turns out that radio telescopes can separate molecules that are closer in mass than typical spacecraft mass spectrometers are able to do, and with less ambiguity. So think of, for example, the case of Titan, where the Cassini mass spec couldn't unambiguously identify that vinyl cyanide. But we can separate better with radio telescopes isotopologues in the atmosphere of some of these moons than a typical mass spectrometer, because it just lacks the mass resolution. But one thing that's kind of skimmed over in this schematic here is the issue of spatial resolution, because these spacecraft missions are going to be in orbit around Jupiter, and they're going to get excellent spatial resolution and study individual terrains in detail. And so if we want to really be able to aid the connecting of observations at different depths within the atmospheres and surfaces of these objects from spacecraft. We need the highest spatial resolution and sensitivity that we can possibly get. So as you saw from the ALMA images, ALMA and the VLA can easily identify large-scale features like the Osiris impact crater shown here, but we're not yet able to get at the smallest features. So we want to be able to resolve something like this, or in the case of Io, a small scale feature, maybe an individual volcano. This volcano I'm pointing at is massive, 200 kilometers across, and big enough that there's some potential to have a spatial resolution element that is smaller than this individual volcano. And this is this sort of resolving individual terrains is the thing that we can start to do now with the VLA for large scale features, and ALMA gets us to a little bit higher somewhat higher spatial resolution, although sensitivity is always kind of an issue as you go to the high spatial resolution. But the ngVLA really would be, because of its sensitivity in particular, would be instrumental in getting down to these small terrains, which are going to very much aid the connection to the spacecraft observations, because we can start to look in localized detail at the same regions from ground-based interferometry and from the spacecraft missions. So hopefully I've convinced you here that the solar system satellites are really intriguing targets in an area where we're going to have a lot of discovery in the next couple of decades. And you should certainly anticipate a big expansion in our understanding of these worlds and in the sort of details of how their surface environments work, both from these spacecraft missions as well as from the next generation of ground-based facilities. Thank you.
So let's turn to questions, and there are a bunch of questions here in the Q&A chat window. So I'll just start with the first one, and basically that asked, why does the UV plot of Ganymede look like two, well, superposed, he calls it airy functions, but basically when you look at short spacings, there is a huge difference between the two maxima. Maybe you can express that, yeah.
Yeah, I would have mentioned that, but I thought it was maybe too technical to go into on the slide. But that's a great observation, and that is just because I plotted both of the sidebands on that plot, and so those two, it's two different and separate frequency blocks that were combined there. And because we're looking at thermal emission, the amplitude at the short spacings it just follows the Planck function for a 130 Kelvin surface.
Okay, thanks. What are the physical and angular sizes of the volcanoes themselves? So that must be on Io. Would there be any chance to detect the thermal emission of the lava with the ngVLA?
Oh boy, that's a good question. The thermal emission from the lava. So I'll start with the first question. The physical sizes of the volcanoes range from essentially unresolvable, even from spacecraft, a meter, let's say, tens of meters, to 200 kilometers. So that one that I pointed out on the surface is a big lava lake that is about 200 kilometers across and is one of the largest regions, volcanic features, at least in terms of the lava. There are much bigger features if you're just looking at the plume deposits. And the angular sizes are challenging to resolve from the ground, but let's say 0.05 arc seconds or something along those lines. If you could go down there, or maybe 0.02, you could start to resolve the individual features. The thermal emission, it's a good question. I mean, I suppose if you had high enough spatial resolution that you were really just looking at the lava flow, then potentially, but otherwise you have so much absorbed sunlight. So at those lower frequencies, you're primarily seeing just emission from the surface that was heated by the sun. So if your pixel includes some lava flow and some non-lava flow, then you're probably just dominated from the passive surface temperature. But it'd be definitely an interesting experiment to do. And whether or not you could detect the thermal emission, what I'd be very interested in doing is looking at Io's lava flows and seeing what you could tell about their thermophysical properties. So there's plenty of wavelengths where you can measure thermal emission, but there are not plenty of wavelengths where you can potentially see into or through a lava flow. I don't know, or you can try to figure out what their densities are, how smooth their surfaces are, things like that. And that's where the radio wavelengths are really what you need, but it's the only way that you can do those types of experiments.
Maybe you can address when you see, for example, a big eruption, could that tell you something about the temperature of the erupting lava? So that's not at the radio, but.
Sorry, I'm not sure I understand. You're asking not about the radio?
Yeah, so when you have, to basically get to the temperature of the erupting lava, when you would have a big eruption, maybe you can determine the temperature via other wavelengths?
Yeah, so in terms of getting the temperature of the lava, the best wavelengths to look at are really the infrared, because the lava, when the magma itself is probably 1500 Kelvin or more, and so the peak of the emission and where it stands out most strongly in contrast against the disk is in the infrared, let's say 1 to 2 microns. And so that's where you really want to constrain the peak of the emission. And if you can constrain the peak of the emission, you can say something about the lava composition, the magma composition, and hence the state of the mantle, composition of the mantle. And it's interesting, so people have been trying to understand what the lava composition is for a long time. We think it's silicate, but which type of silicate are we looking at? What composition of silicate? And lava temperature is one way that people try to answer this question, but you get really complementary information from looking at these thermophysical properties that you would get at the radio wavelengths. So conductivity, density, heat capacity, things like that can give you quite complementary information to the magma temperature that can maybe combine to give you a better constraint on composition than you could just from the infrared temperature alone.
Thanks. There's another interesting question. Can you say something about the possibility of life on Enceladus and Pluto?
Enceladus and Pluto. So is that just commenting on, can I clarify, or whether the VLA or ngVLA would?
I think it's just a question that this person is interested to know if there could be life on Enceladus and if there could be life on Pluto.
So Pluto is tricky. I'm going to address the easy one first. There's certainly a lot of interest in the potential for life in the ocean environments on Enceladus and Europa in particular, but any of the ocean worlds could potentially have a habitable environment in their ocean. There's a lot of unknowns. We don't know whether there's a sufficient energy source in any of these cases, and crucially, we don't really know what the oceans are composed of and whether you have the material that you could build life out of. Enceladus has gotten a lot of interest recently, not necessarily because it's the most potentially habitable environment, but it's the environment where the ocean is directly observable because it's coming out of the South Pole through these plumes. And so you can actually study the ocean through these plumes and try to figure out what the ocean is made of and whether it's habitable. I'd say it's still a big open question. It's not inconceivable. But there are a few problems. For example, the stability of the ocean, whether the ocean stays frozen for long enough to actually evolve life. But there are many people who want to go back and explore Enceladus, and there's a lot of very interesting mission proposals that would try to answer that question better. Pluto, I'm not sure that I have anything bright to say about the potential for life on Pluto. It's very cold.
That's fine. So the next question, what type of physical changes to the material do you expect from the weathering by high velocity electron impacts like on Ganymede surface?
Yeah, so it's complicated, and that's part of the problem. You know, I showed those temperature residuals, but linking those back to processes is challenging. So the electron impact, you have a variety of different processes going on, and they act in opposite ways. So you have surface bombardment, and that can get down to some depths within the surface, and that's not super well constrained. So you could potentially have sputtering processes where you release material from the surface, slowly erode the surface. It could make the surface more porous. You could actually have chemistry that's affected by this bombardment. But in terms of the physical properties, the things that we can really measure, like conductivity and density, are the sorts of things we can constrain. And the electron bombardment can break up the surface, but at the same time, it can help center the surface, which means that you have the grains, an increase in the contact area between the grains, which can potentially increase the density and conductivity. And so electron impact can have these competing effects on the surface, and it's not really clear yet from models or observations which of these would be the dominant effect that you see.
So another question. Does the thermal model consider the material of the surface, or it's the part considered later in the residual? So I guess they want to know if the surface materials are included in the model or not.
Yes, the surface materials are absolutely included in the model, and they actually make a really big difference. And by the way, a big source of uncertainty in the model is the fact that we don't have a lot of laboratory data at the relevant wavelengths. So if anybody works in a lab that can make measurements at these wavelengths, I have a lot of requests. But so for the models, for the icy satellites, what I've assumed for my models at least is a porous, dry snow with meteoritic dust. So dry snow is very transparent to the surface, but you need some sort of contaminating material. You look at Ganymede's surface, it's dark, but it actually is mostly ice. It's mostly porous ice. It's just kind of dirty, porous ice. And there aren't a lot of good laboratory analogs for that, looking at the surface properties as a function of which contaminants are there, how much contaminants, how dense the surface is, how porous. It's roughly the same as how dense. So that goes into the model, but you also have to include the dielectric properties of the material in the model, which go into that, the like part 3 in my 1, 2, 3, which determines how deep into the surface you see. So the dielectric properties just to dictate how the photons are interacting with the surface and how attenuated they are. And again, with these porous ices, that you see very deep into the surface. Hopefully that answers the question.
So and then something that is related to one of the earlier ones, will the locally generated high energy particles always dominate over the solar wind, or will larger solar flares end up producing different local fluxes? That is, will there be a value to target of opportunity observations of Jupiter and its moons when large solar flare ejecta passes nearby?
That is a great question, and I don't know the answer to it. Imke may have some more insight.
Well, the satellites are all well embedded in the magnetosphere, magnetic field of Jupiter. So there's no direct connection between the solar wind and the satellites. However, the solar wind, certainly flares, will affect the particle distribution in the magnetic field. So it definitely would be useful to target observations when a large solar flare has happened. I mean, for example, certainly in the Earth magnetic field, sometimes when there are large solar flares, you can see sort of another kind of radiation belt evolve and be produced. So for a while, there may be just a an additional, what we call radiation belt, a belt with high energy radiating particles in the magnetic field. And so similarly for Jupiter, indeed you might expect processes where solar flares would affect the particles and the magnetic field of Jupiter.
Thank you.
So another one, and that is, let's see, will the ngVLA satellite tracking be needed to make full use of the explorers? And that may be more for one of the ngVLA people, for Alberto or Eric. I mean, the satellites will be tracked. I mean, when you observe one of the satellites, they will be tracked, of course, by the ngVLA. But I'm not sure if that is really the question that was asked here. Then there is another one, well, one that I will answer here, whether the papers will be available on arXiv, and they will be. They're not, they're not there yet because they aren't accepted yet. And then another one is, what about comet investigations with ALMA and the ngVLA?
Right. So, of course, there are a lot of targets in the solar system that you can do a lot of with ALMA, as well as the VLA and the ngVLA, and comets, because of all of the molecules that you can detect and the chemistry that's going on, have been a really fruitful avenue for observations with ALMA, where ALMA has observed and mapped several species. And you know, I'm not an expert on the comet spectroscopy, so I'm actually not sure which species will be detectable with the ngVLA if you can do the spectroscopy, but absolutely if you can detect them in thermal emission, and especially if you have one that's nearby and warm and bright, you could imagine using the higher sensitivity and spatial resolution of the ngVLA to do that mapping much better at a greater detail and separate out potentially the different components of the comet. So comets are very large in angular size, and so you have the potential to get a lot of detail with the sensitive high resolution instruments. And if someone else wants to jump in on some of the spectroscopy science, they are welcome to.
I think indeed comets, I mean, both ALMA and the ngVLA, they will be great assets to comet science. So that's no question about. I mean, nowadays you can already observe some lines with the VLA, but with the ngVLA, that will be 10 times higher sensitivity and spatial resolution.
And I'll add that for many of these species, it's very helpful to get lines at different frequencies that have different excitation energies. That gives you a much stronger constraint on the properties of the gas that's producing the emission. So if there are species that you can currently detect and resolve with ALMA, looking at the same species with the ngVLA is still very valuable because you're detecting the different excitations.
Yeah, and also you can use both ALMA and the ngVLA and the VLA to also probe the nucleus and look down into the nucleus. Most likely the subsurface temperature is much, much colder than the surface temperature of a comet. Well, let me thank Catherine again. And also I'd like to thank all of you who have listened in and asked questions. So I think with that we can end this really interesting talk.
Thank you.